And Lorenzo, the floor is yours.
Okay, great. Can you all see my screen? Yeah. Okay, so this is going to be a quite applied talk, hopefully fairly new to the most of you. So I'm going to talk about agent-based modeling and SMC² for bacterial colonization. And this is, of course, a joint work with Paul and Chris. So the outline of the talk are the following. I will start with an introduction explaining the what, why, and how of the problem. Then I will move to the model that is used to model the spread of the bacteria in our population, which I call the UC model. And precisely, I will show you the stochastic process that model the spread of the bacteria, with a particular focus on the way in which we model the transmission rate and likelihood. Then I'll move to a section about inference, where the main algorithm for inference is this SMC². And just, to introduce this SMC², I will also introduce SMC. I will just recall SMC for completeness. And after that, I will talk about the experiments, and so the kind of data that we have, which I will also introduce in the introduction. The synthetic population, meaning that given that these data are sparse in space, we will draw some synthetic data to sort of complete the population. And then, of course, I will conclude with some results and with a brief discussion. So let's start with the what of the research. So what we want to do in here is to understand the transmission to humans of antimicrobial resistant bacteria. And precisely, we have these data from the African country, Malawi, on extended spectrum beta-lactamase bacteria, and precisely Escherichia coli and Klebsiella pneumoniae. And of course, the question that we want to answer are multiple, like, for example, where is the biggest source of infection coming from? Is it some kind of hygiene problem in the household? Is it something more related to the environment, like, some problem with the sewer system or stuff like that? Of course, if it's seasonal, and so if it changes across, the months in the year, if there are any sensible area geographically, and so if there are any suggestion on where to act to sort of reduce the spread, and also if there is some kind of a relation with the individual covariates, so if age, income, and gender can somehow influence the spread. The why, of course, is very simple, as in these epidemiological applications. So we just want to understand the spread of these bacteria to avoid people feeling unwell. So pretty simple to motivate. And the how is just going to be a sort of other outline of the talk. So essentially, as I said, we have these data on E. coli and cave pneumonia. And these data are both sparse in space and in time. And they consist of some test results on the bacteria, some locations of the individuals, and some individuals' features, which consist of an household number telling us if an individual is in a certain household or not, age, gender, and income. And the key steps are define a stochastic process that model the spread of the bacteria, and of course compute associated likelihood. Then sort of complete these sparse data with a synthetic population, just to model the dynamic of the spread of the bacteria properly. Then infer the parameters and, of course, draw some conclusions. So let's start with defining the stochastic process. So we have a population of size Ni, so we have Ni individuals, and we say that these random variables CTK model the state of individual K at time t. And precisely, we can model it as a Markov chain where, there is only a dependence on previous state. And according to that, we will have, a rate that allows us to go from susceptible to infected and from infected to susceptible in terms of recovery. And given that we are modeling bacterial colonization, I call it UC model instead of SI model, because, we are modeling colonization and uncolonization. And just to be sure that I have stressed this enough, we are going from uncolonized to colonized with this rate, lambda T delta K, and we are going back from colonized to uncolonized with this recovery rate gamma. And as you can see, we are considering an agent-based model because the transmission rate changes with the individuals. As I mentioned before, the data consists of also some household numbers. And so what we know is also that the individuals are in a certain household. And so that's why I'm just saying that we have these NH households that just induce a partition over the index, over the individual's index set, meaning essentially that an household can be simply represented as a set in the partition, telling us, which individuals belong to this to that household. And in terms of notation, I will just use capital letters for a generic household and HK for the household of individual K, where this notation is overlapping with, of course, for example, an HK prime if K and K prime are in the same household, but it's just, to have some kind of mathematical formulation. So the main part of the modeling is definitely the transmission rate, because the recovery rate here is assumed to be constant across the population and in time.
Lorenzo, can I just ask a question to clarify? So you're matching this in discrete time, although you have rates.
Yeah, in discrete time. It's a discrete Markov chain, discrete time Markov chain. Okay. Okay, so it's worth it to spend some time on the transmission rate, and precisely we want to try to include all the information that we have in this transmission rate. So something about the individual covariates, something about the individuals in the same household, something about the individuals across the different households, and something about the seasonality. So if we look at this, element specifically, we have that the individual covariates effect is something that looks like this. So just e to the power of a linear combination of the covariates of the individual K, where of course what we want to do is to estimate the coefficient of the covariates. About the within household effect, what we have is a parameter that scales this effect. And then we have here we are just counting the number of colonized individuals inside the household, and either normalizing it or not with the size of the household, which means that we are either considering the absolute number of colonized individuals in the household or the prevalence in the household. In terms of the seasonal effect, we are just considering an oscillating function, which is just somehow modeling the way in which we have an increase and a decrease in the transmission. And of course, we will choose frequency and phase in such a way that they match the seasons in our country. So given that we are considering Malawi, we know that there is a dry and wet season in Malawi. And so for this reason, we'll use some numbers for frequency and phase that match that kind of oscillations. And finally, we have this across household transmission or cross household effect, which is again a parameter beta2 multiplied by something that depends, of course, on the prevalence or absolute number of colonized individuals in each household, scaled by some coefficient that decay in space. And so in this case, we are just saying, okay, if an household is very close to the household of individual K, then we'll have somehow we will be more affected by that household. Otherwise, we will be less affected. And in terms of spatial kernel, we use this formulation. So either an exponential decay or a Gaussian decay. Okay, now let's talk about the likelihood, which relates our data with the latent process. So as I said, we have some data that are collected sparsely, both in time and in space, meaning that they are sparse in time because we have tests every 2 weeks, more or less, and in space because we collect, not all the individuals inside the population, but just a very small subset of it. So what makes sense is to use a subset of the individual indexes to model, the individuals who are going to be reported at that time. And so we'll use this notation RT for those individuals. And moreover, we add also an extra layer of noise, which are these Bernoulli, which just take into account false positive and false negative in our tests. And of course, if the individual is not in our reported test set, then we'll have a not available number. Of course, from here, we can compute the likelihood like this, but this is going to be very difficult. So because we have to marginalize out the whole population. But we know that given that we are considering some YTs that are conditionally independent from all the CTs, and CT is a Markov chain, we know that this is an HMM. And so we have a pretty straightforward way of estimating the likelihood, which is through SMC. So just to summarize this section, we have presented an agent-based model for the spread of antimicrobial resistant bacteria, where we consider a transmission rate that change across the individual. That's why it's agent-based. And in this transmission rate, we consider multiple informations, like a within household effect and a cross household effect. And of course, this cross household effect depends also on the household distance, the individual covariates, and some kind of seasonality. And then we have presented also a likelihood function, which is defined on our sparse data and also takes into account false positive and false negative. So let's now talk about inference. So how do we inference the parameters? Maybe I didn't say that properly, but the parameters that we are looking for are beta 1, beta 2, phi, delta, and alpha, where beta 1 and beta 2 are the within and across household parameter. Phi is something that is used in the spatial kernel to just control the decay in space. Delta is the covariates, are the covariates coefficients. And alpha is just something that control, how we jump from one season to the other. Okay, so hopefully now it's clear what the parameters are and the meaning of the parameters. And additional quantities, which in this case are considered as fixed. So frequency and phase because of the wet and dry season in Malawi. So we sort of choose them in such a way that they match that oscillation. Gamma, which is just the recovery rate, which was fixed to 1/10, so about 10 days from previous studies, and sensitivity and specificity, which were fixed according to some studies over the test that we have over the bacteria. So of course, the big problem in here, as I said before, is the computation of the likelihood, because we need to marginalize out the whole population. But as I said, one possibility is to use SMC to estimate the likelihood. So just to fix some convenient notation, we will say that this is the initial distribution of our latent process. This is our transition kernel for our latent process, and this is our emission distribution. So if we fix this notation, then an SMC is just something like this. So we have some data, we have some proposal distribution for our latent process, and then we have some particles. And what we're going to do in a general time step is to just propose some new outcome from our latent process, then weight this outcome according to all these quantities, and then resample according to these weights, which are intuitively just telling us, let's choose the best and the best outcome among the one that we sampled. And of course, from here, we have a simple estimate of the likelihood, which is given by this. So if we want to look at the flow of a general t-time step, just to stress this in an SMC, we have a parameter that is fixed. Before actually performing the time steps t, we resample our latent process, then we sample a new latent process at time t, then we estimate the likelihood up to time t, and then we go to the next step. But of course, in here, the theta is fixed, so we are not really inferring the parameters. So ideally, we would like also a technique that tells us if we want to keep or if we want to sample some new thetas. And that's mainly why we have chosen to use SMC². Of course, another option could be to use particle MCMC, and so use the estimate of the likelihood in MCMC to infer the parameters, but we want to do it sequentially. And so that's why we decided to use this SMC². And just to talk briefly about SMC² and give you more or less the intuition on how this algorithm work, we have again some data, we have again some proposal distribution, we have some particles for the epidemics and some particles for the parameters, and of course a prior over the parameters and a proposal for the parameters. And what we're going to do is to start by sampling from the prior multiple combination of our parameters, and then per each combination of parameter, essentially we are running an SMC. And so per each time step we are proposing some new latent process realization per each parameter, and then we are resampling according to the weights. But of course, at the end of each time step, we have also some kind of check on the quality of the parameters that we are using. And if the parameters are somehow bad, then what we are going to do is to resample the parameters and then accept or reject the new parameters. So if we want to compare the SMC² flow at time t with the previous one, we'll see that now we have multiple combination of the parameters theta. What we're going to do before the time step t is to resample all the latent process at time t-1, and we are going to do it for all the combination of the different combination of the parameters theta. Then we are going to sample a new latent process realization. Then we are going to evaluate the likelihood, and depending on this, we will decide if keeping theta or sample new theta and compare these new thetas with the old thetas, and then go to the next step. So to summarize this section, so what we did was to just show that the way in which we have built the UC model is an HMM, and so we have well-known technique to estimate the likelihood. And in particular, I introduced SMC to show you how to estimate the likelihood with SMC. But that was just to introduce the actual inference algorithm, which is SMC², which is just a sort of more complicated version of SMC, where we are intuitively running an SMC for the parameters and an SMC for the epidemic. Okay, let's now talk about the experiment. So of course there are other people involved in the project, people who collected the data, people who work on the data before me, and also people who prepare the code, some part of the code that I've used to fill the synthetic population. So it's worth it to mention them and to thank them for their work. So let's talk again about the data, just to make sure that you understand the kind of data set that we have. So as I said, we have some data from this African country, Malawi, and precisely we have three areas of study, which are Chihuahua, the blue one, Chileka, the orange one, and Indirandi, the green one. And each data point consists of some test results on both the bacteria, E. coli and Klebsiella pneumonia. Of course, we have an household number for each individual, telling us which individuals are in the same household, and a location, which is locating in space the household. And of course, also some individual covariates, and in particular, we focus on age, gender, and income. And you probably don't know that, but this is a very, very sparse version of these aerial studies. So there are way more households in these cities. And of course, if we use just this sparse version, we cannot really simulate the dynamic of the epidemic. And it might be that most of the parameters are going to be, underestimated, or anyway, we will get a very biased estimation of the parameter. So the idea was to create a synthetic population algorithm, which is just filling the aerial study with some synthetic households. And these synthetic households are obtained from other geographical studies. So essentially what I'm doing is running the algorithm to fill, this area of study with other households. And if the households are incomplete in terms of individuals, I will try to sample some individuals with similar features to fill, the synthetic households. And of course, now you can see that these area of study are way more dense in households, and they look way more like the real areas of studies. Okay, now it's probably almost time to conclude. So I will briefly talk about the SMC² output that we got and a brief interpretation. So so in here, I'm showing you the final posterior estimate over beta1, beta2, and phi parameters. So essentially, I'm just looking at the last time step of the SMC² and plotting histogram and KDE estimate of it for the 3 years of study. And you can see that in here, in the coli at least, we have pretty good estimate with peaky posteriors, but in Klebsiella it was a bit more tricky, and indeed for Indirandi and Cileca we have quite flat posterior. But anyway, that's the best that we got so far. And the takeaway messages of the experiments are the following. So we noticed that firstly, some of the parameters were not really easy to estimate, or somehow, not really useful. For example, the individual covariates were really, really close to 0. So what we tried to do was to just fix all those covariates to 0 and, rerun the model without the covariates. And we obtained a better likelihood score. So we decided to keep that kind of simulations. And also the seasonality, we were really bad in estimating the seasonality because we got really, really flat posterior. So what we decided to do was to just, running multiple simulations with different values of the seasonality and just choose the best one from a likelihood score point of view. And we obtained that the one with the highest seasonality were the most interesting. So with a seasonality coefficient, an alpha, that it was around 0.8. In terms of the kappa thing, which were just telling us, if considering the prevalence or the absolute number of colonized individuals within and across household transmission, we find out that for E. coli, kappa1 was better as H, so it was better to choose the prevalence, while for the Klebsiella pneumoniae, it was better to use the absolute number of colonization for Chihuahua and Indirande, but the prevalence for Cileca. And here I'm a bit speculating, but the interpretation could be something like E. coli is more something that is more a bacteria that stay in the environment, while Klebsiella is spreading through droplets, and so it's mostly related by the individuals. And so that's probably why we have this prevalence in here and this, absolute number of individuals in here. While for, yep.
1 second. You say better in terms of predictive performance, or in what terms?
In terms of likelihood.
Right. Okay.
Okay. So just a higher likelihood score.
Okay. Gotcha.
And in terms of kappa2, we find out that the prevalence was choosing the prevalence was the best way to do it. And again, I'm sort of speculating here, but it also sort of makes sense because we are, in that case, we are modeling contacts across households. And just to conclude, the exponential decay was preferred to the Gaussian decay, but I mean, I don't really have an interpretation for that. Okay, now I just want to show you before concluding some useful plots, like for example, the exponential decay in space of the 2 bacteria. So you can see that there is a quite fast decay in Klebsiella and Klebsiella pneumoniae, and a quite slow decay in Escherichia coli, which again might be because this is more about the individuals and this is more about the environment. We can also do some kind of mean over time and over particles of the number of infected of colonized individual in space, and we can sort of look at, you know, what are the hotspots in space. And of course, we can also sort of estimate the RT and understand, you know, which are the most affected period of time in the year. So just to conclude, we have proposed an agent-based model to model the spread of AMR bacteria in a population. And of course, we have used a transmission rate that try to use all the information that we have in the data. The cool thing is that the parameters have some kind of straightforward interpretation in terms of their use. And we use SMC² to infer the posterior over the parameters, which is a fairly new technique in epidemiology. And we showed also a couple of tools that might be useful to, you know, reduce the spread of the bacteria, or at least that's what we hope. As for Alice, I don't have a paper, but the paper is on its way. We are writing it. And thank you very much for listening.